the last week or in the last lecture, basically we discussed about the finite control volume analysis and build a basic knowledge about the finite control volume analysis. And starting with that, we developed the continuity equation based on the Reynolds transport theory. And we discussed different applications of the continuity equation and solved different problems related to the in the end of the moving volume. For moving control volume velocity instead of do it as a parameter in the continuity equation or what that will be uh, relative velocity. So today we are going to solve two problems related to the moving control volume. One is related to the moving control volume and other is related to the moving as well as the deforming control volume. So we'll see how we tackle the problems related to the moving control volume as well as the deforming control volume. So we start with the first problem. So in the first problem, we have an airplane that is moving at 971 km/h as shown in figure. The frontal intake of this airplane. Did we solve this problem in the last lecture? आवाज आ रही है जी आप लोगों को?
Yes, sir.
There is an airplane that moves at 971 km/h. The frontal intake of this airplane is 0.80 meter square. By the frontal intake, we mean that the area of this engine, the intake from this engine is at 0.80 meter square, and the air entering this engine has a density of 0.736 kg per meter cube. There is an observer on the ground, and it observes that the exhaust gases, that this includes the exhaust fuel gases, they leave the engine with a area of 0.556 meters. So that is the exhaust area or the discharge area here is 556 meters square, and the velocity is 1050 km/h. The exhaust gas density is 0.515 kg per meter cube. We are required to calculate the mass flow rate of the fuel into the engine. That is, at what rate the fuel is being injected into the engine. So we can easily see that it is a problem related to the moving control volume. So we'll start with the concept of the continuity equation. So we'll write down the continuity equation. The continuity equation is partial by partial T integral over the control volume rho d plus integral over the control surface rho v dot and the a equals to 0. Since it's a steady state process, it is happening continually. There is no change in properties with respect to time, so we can mark this first part as 0 because it's considering the steady state effects. It's considering the unsteady state effects only. Now, for the second part, we know that it's a moving control volume. So instead of V, we need to use W here. So we'll write rho W dot NDA. And if we see the problem statement, we can see that there are two inlets, that is the fuel injector, the air intake, and one outlet, that is the exhaust gas discharge. So basically we have three control surfaces. Two are the inlets and one is the outlet. And we can see that they do not have any variation. They are fixed areas. The velocity is not varying with area. So we can just write it as a simplified continuity equation, that we can write that because fuel is being taken in, so it would be negative minus m dot n of, that is for the fuel, minus at section 1 rho 1 W1 A1 plus rho 2 A2 W2 should be equal to 0. in this statement, we know row 1, we know A1, we know row 2, we know A2, but we don't know W1 and W2. We can calculate these. They are shown in this picture here. But how W1 and W2 are calculated for a moving control volume, that is of a concept. Basically, W1 is the rate at which the air is entering the control volume from the frontal intake. So what would W1 be? It would be equal to the velocity at which the plane is moving forward, but in the opposite direction, right? So we can write it as minus 971 kilometers per hour. The other velocity that is at the discharge should also be W, which should not be the absolute velocity. In fact, should be the relative velocity. And we know that the exact velocity, the absolute exact velocity is 1050 kilometer per hour. But this is the absolute velocity from a perspective of an observer that is on the ground. That is an absolute velocity. But we also know that the plane is moving forward with a velocity of 971 kilometer per hour. So what would be the relative velocity? It would be sum of these two velocities, right? 1050 plus 971. Clear? So now in our equation, which we have written here, we know all the values. Just the unknown is m dot n. So we can solve this for m dot n. M dot n would be equal to row 2 A2 W2 minus row 1 A1 W1. Clear? ठीक है, समझ आ गई? वैल्यूज डाल के बस अब कैलकुलेट करना है इसको. Is it clear to everyone? कोई क्वेश्चन तो नहीं है इसमें? आवाज आ रही है क्या आप लोगों को?
यस सर.
तो फिर समझ आ गई है प्रॉब्लम की, इसमें कोई क्वेश्चन तो नहीं है?
नो सर.
Okay, good. The next problem is a very interesting one and a very important one. If you understand this, I will believe that you have gathered the basic concept or major concept of the continuity equation and the moving and the deforming control volume as well. So if you are able to solve this problem, you will be able to solve different problems or the difficult problems related to the concept of the continuity equation and the moving and deforming control volume. So in this problem, basically we have a syringe that is used for inoculation, that is just to pinch someone or for inserting the fluids into the body. You all have seen injections or syringes. The plunger of the syringe has a face area of 500 millimeters cube, that is this plunger here. This has area of 500 millimeters cube, this plunger. The liquid in the syringe is to be injected steadily at a rate of 300 centimeter cube per minute. That is the volume flow rate of this liquid exiting from the syringe or the needle is 300 centimeter cube per minute. There is also leakage from this syringe. there is a leakage past the plunger that is 0.1 times of the flow rate out of the needle, that is this leakage fluid from here. And here is Q leak, and it is equal to the 0.1 into Q2, that is 0.1 times of the 300 centimeter cube per minute, that is 30 centimeter cube per minute. You need to determine the speed of the plunger in order to produce a flow rate of 300 centimeter cube per minute. So you need to calculate the velocity. Now, what's unique in this problem is the control volume fixed? क्या control volume fixed है इसमें? Is the control volume fixed?
No, sir.
It's moving. Move कर रही है.
So plunger motion के साथ करेगी.
Yes, as the plunger moves the control volume also decreases in volume, right? उसकी वॉल्यूम कम हो जाएगी, उसका मतलब कंट्रोल वॉल्यूम मूव कर रही है. प्लस जो ये कंट्रोल वॉल्यूम है वो डिफॉर्म भी कर रही है, क्योंकि जो फेस प्लंजर के साथ अटैच है, जो कंट्रोल सरफेस प्लंजर के ऊपर ड्रॉ किया हमने, तो वो भी तो मूव करेगा, डिफॉर्म करेगा, राइट?
Yes, sir.
So it means it's a deforming control volume. So we need to write the continuity equation in the most generalized form, that is partial by partial T integral over the control volume rho dV plus integral over the control surface rho V dot and dA equals to 0. What about the first term? Will it be 0 this time? Will it be 0? क्या ये 0 होगी?
No, sir.
No, it will not be 0. We need to evaluate it. What about the second term?
Yes, sir.
No, it will not be 0. It is basically representing the inflows and the outflows, right? So what is the inflow? There is no inflow in this control volume. There is only outflow from the needle and the leakage point from here and here. And that is also through fixed areas, because we are given the volume flow rates. We can just write this term as Q2 multiplied by the density, right? Plus this Q leak into density, that is 0.1 times rho into Q2 equal to 0. And this term would be brought here as it is. Clear? ठीक है, समझ आ गई?
Yes, sir.
Now we evaluate this term, the first term. First we consider the integral, just the integral, not the derivative for the timing. Integral control volume rho dV. If density is considered constant or fixed, or this flow is incompressible, then we can write this integral as rho integral control volume 1 dV, right? ऐसा ही है? And
yes, sir.
then this integral would be equal to the volume of the control volume, right? Rho volume of the control volume. ऐसा ही है?
Yes, sir.
And the volume of the control volume is composed of two volumes. That is the volume of this cylinder this region and the volume of the needle. ऐसा ही है?
Yes, sir.
So we can write it as volume of needle plus volume of cylinder क्या होगी जी? Any idea about volume of cylinder क्या होगी? किस तरह लिखेंगे?
Pi r square L.
एरिया ऑफ प्लंजर हमें गिवन है, राइट? Area of plunger multiply by its length, the length of the cylinder, right? So AP into length. Clear है यहाँ तक? Now we take the time derivative of this integral, ताकि हमारी first time हमें directly मिल जाए partial by partial t integral control volume rho dv should be equal to partial by partial t derivative volume of needle plus AP to length. In this equation, will density change with time? क्या change होगी density time के साथ? Density time के साथ change नहीं होगी, so it is constant, so we can bring it out. So rho volume of needle change होगी time के साथ?
Yes.
नहीं, क्यों change नहीं होगी volume of needle?
Fixed up.
Because needle is a fixed thing, उसकी तो volume change नहीं हो सकती. So टाइम डेरिवेटिव जब हम वॉल्यूम ऑफ नेडल पे अप्लाई करेंगे तो वो भी 0 हो जाएगी, ऐसे ही है? क्या एरिया ऑफ प्लंजर चेंज होगा टाइम के साथ?
No, sir.
So एरिया ऑफ प्लंजर विल बी ब्रॉट आउट. लेंथ चेंज होगी टाइम के साथ?
Yes, sir.
Yes, that length is decreasing with time, right? Partial L by partial T. Clear?
Yes, sir.
Now if we see, okay, just write it on a side here. What is happening basically? Distance is velocity into time, right? And in this case the distance is negative because it's decreasing, right? So the displacement is basically decreasing. The change is negative dl, and if v is the velocity of the plunger and time is delta t partial t, so vp would be equal to minus partial L by partial t, right? Or partial L by partial t is equal to minus p, minus vp. Clear?
Yes, sir.
So this equation can be written as, so the integral partial by partial t integral over the control volume rho dv is equal to minus rho AP right?
Yes, sir.
So we have simplified the first part here. Also, we can write minus rho AP into VP plus rho Q2 plus zero point 0.1 rho Q2. If we see rho is constant, so we can just eliminate it from the equation. So we'll just get AP VP equal to 1.1 times of Q2, right? Or VP would be equal to 1.1 times Q2, which is the required parameter from the question. VP was to be calculated. So we have developed the equation for calculation of VP. We know Q2 and we know AP. Will just plug in the values and we'll get the answer. Clear?
Yes, sir.
Any question? Anything that you couldn't understand or you couldn't comprehend?
No, sir.
Okay, good. So with this, we have completed the continuity equation. The next equation that we will be developing would be the linear momentum equation. We have already discussed linear momentum equation in the last chapter, that how linear momentum equation is achieved from the Reynolds transport theorem. Basically, if we put B equals to the small b equals to velocity in the Reynolds transport theorem, we get the momentum equation, right? And capital B becomes mass time velocity, which is basically equal to the time rate of change of, which is basically equal to momentum. And if we write the Reynolds transport theorem for this, then we get d p by dt equal to partial by partial t integral over the control volume rho. Now in Reynolds transport theorem, here we have small b, so we're writing the velocity vector here, dv plus integral over the control surface rho into b, that is small b again, so we'll have velocity here into v dot n, the velocity vector by dot product of unit area normal vector into dA. So this is basically your momentum equation. What is time rate of change of momentum? You would have studied this thing. Time rate of change of momentum क्या होता है? आपने पढ़ा होगा इसको कहीं पे.
Force.
Yes, time rate of
Force.
momentum is force. So basically the result of the momentum equation is the net force that is acting on the system because of the change of momentum, or the net change of momentum is equal to the net force acting on the system, right? So basically by solving this equation, what we will be getting is a force vector in the net form, that is this force vector would be fx I. So momentum equation will have three equations: the x component, the y component, and the z component, because it's a vector equation. Momentum equation, unlike the continuity equation, is a vector equation. Clear? So continuity equation तो हमारे पास स्केलर थी ना, उससे हमारे जो रिजल्ट्स आते थे they were scalar results, but the momentum equation is a vector equation. So इसके हम तीन components लिख सकते हैं: x component of the momentum equation, y component, and the z component. Clear है?
Yes, sir.
So momentum equation is nothing but the statement of the Newton's second law of motion. That is, the rate of change of momentum of system is sum of all the external forces acting on a system. It is the mathematical description of this law, that the rate of change of momentum of system is the sum of all the external forces acting on the system. So all the forces that are acting on the control volume or coincident control volume are the control volume forces, or they are the system forces. So the control volume forces acting on the control volume are basically the forces acting on the system. They should be equivalent. Clear?
Yes, sir.
So the first term in the momentum equation, that is this term, which I have highlighted, is the rate of change of momentum of the contents of the control volume. That is what is happening inside the control volume. What is happening to the components of the control volume. And the second term, that is this term, is basically the net rate of change of momentum through the control volume surface. That is what is happening at the surface of the control volume. How the momentum is coming into the control volume and how it is going out. Clear?
Yes, sir.
So the forces involved in the linear momentum equations are basically two types of forces: the body force and the surface force. What is the body force? बॉडी फोर्स कौन सी होती है जी? व्हाट इज फोर्स ऑफ योर बॉडी? क्या कहते हैं उसको? ये तो अब तक पता लग गया होगा बॉडी फोर्स. ये इज द फोर्स ऑफ ग्रेविटी और weight of the body is the body force, and the surface forces are the forces that are acting, because pressure force is a surface force. The force due to some weight on you is surface force, right? So only in momentum equation we are basically dealing with the body forces and the surface forces. So the only body force that is considered in this course is the action of gravity, and the surface forces are basically that are exerted on the contents of the control volume by the material just outside the control volume. So we need to just understand this integral. Basically we need to understand this product here, which I am encircling in red. We need, in order to solve momentum equation, we need to understand this thoroughly, because what this term is representing, this is basically representing the net momentum flow into the control volume and out of the control volume. So if the momentum flow is into the control volume, will it be a positive term? If the momentum flow is out of the control volume, will it be a positive term or a negative term? तो हमें वो साइन समझने जरूरी है. So we can understand that with a very simple, इसको मुझे अगर समझना हो तो ये फिगर है. We'll discuss this figure in the next class. Basically what is this figure is representing, और कैसे हम जो है इस टर्म जो हमारे पास ये इंटीग्रल की टर्म है इसको डायरेक्टली सिंप्लीफाइड साइन के साथ लिख सकते हैं, बजाय इसके कि हम हर बार इसको वैल्यूएट करें. हम किस तरह से इसको सिंप्लीफाइड करके लिख सकते हैं. ठीक है? ऑल क्लियर?